This is the summary for lesson 7, which was representations of linear relationships. And so they begin with this summary talking about they talk about the marbles and the volume of water in the cylinder. And they described it as measuring the height. And if you remember that very first activity, we observed that the height was proportional to the volume. So you could look at the height, measure the height, and that would tell you what the volume was because they were proportional. But then we went on to realize if you had a different shaped container, then the volume was not proportional to the height. So you needed some other way to measure volume. And that was based on the number of marbles that were added. So when you drop marbles into the cylinder or any other container, what you're measuring is volume, not the height. So it says here we can watch the height that's measured by the volume. So we're really looking at the volume of the water increased by the same amount. It increased by 3 milliliters for each marble that was added. So this constant rate of change means there's a linear relationship between the number of marbles and the volume of the water. So that y-axis is labeled volume and it's not labeled height. So I'm looking at the relationship between the marbles and the volume of the water. Add one marble, the volume goes up 3 milliliters. It's true that in the cylinder, the height does go up, what's measured as 3 milliliters. But what you're really looking at is the relationship between the marbles and the volume. Add 2 marbles, the volume goes up 6 milliliters. Add X marbles, the volume goes up 3x milliliters, 3 times the number of marbles. So as we look at this, the volume, which is Y of the water for X marbles, is Y equals 3 times the number of marbles plus the beginning amount of 50 milliliters. Now in the activity we use 60 milliliters, but in this particular explanation they're going to use 50 milliliters. Any linear relationships can be expressed in the form of y equals mx plus b, and we're going to get to why that's an m there, and why that's a b there, using just the rate of change, which is m. So one question is, why use m for the rate of change? So the rate of change was 3 milliliters for each marble that was added. So that's the rate of change, 3 milliliters per marble. And the initial or the beginning amount, so that's going to be this b, is where we start. So that's the beginning amount. The 3 represents the rate of change or the slope of the graph, and the 50 represents the initial or beginning amount or vertical intercept of the graph. So let's take a look at that in a little bit more detail. Here's the graph. As you add a marble, what happens to the volume? Add another marble, what happens to the volume? Add another marble, what happens to the volume? So in each case, you add a marble, the volume increases 3 milliliters. Add another marble, the volume increases another 3 milliliters. Add another marble, the volume increases another 3 milliliters. So the volume is moving. So we can think about that m as the slope as moving. Now I looked up why use m. There's really no good answer of why mathematicians started to use m for the slope, but one person suggested, well, maybe it's because it moves, and it does move. It's a measure of how much movement there is in volume for each marble, and that movement is 3 milliliters in volume for each marble that's added. And the beginning amount, once again, is 50 milliliters. So using marbles to measure the volume, not height, it's volume that's listed over here, not the height. 5 marbles would equal 15 milliliters. 5 times 3 milliliters for each marble equals 15 milliliters. So if you went out here to 5, then you have to go to the 50, that's the beginning amount, and then you go another 15 milliliters, and you'd end up somewhere up here beyond this straight line up here. So at a final volume of 65 milliliters. So m for the rate of change. So how much is the volume changing for each marble? It's changing by 3 milliliters. For each marble, there is a move, m, of 3 units. And b for the beginning amount. So b we're going to use for the beginning amount, which was 50 milliliters. And so you can write this equation. Y is equal to mx. This is the slope. We're going to use m for the slope because it gives the idea of moving. 3 milliliters for each marble. So 3 milliliters per unit along the x-axis, which is marbles, plus b for where it begins. All right, so y is equal to mx, that's m for move, plus b for beginning amount. The beginning amount is 50 milliliters. The movement is that 3 milliliters. So what if we fill that in? So the 3 is the slope or the movement, so 3 milliliters for each marble. And the 50 milliliters is where you begin. So this is the equation. Y is equal to 3x plus 50. Well, let's say that x is equal to 2 marbles. So you go out here to 2 marbles. What's the coordinate? So the x coordinate is 2. So what's the y coordinate? So you go out here for 2. Then how far do you go up for that y coordinate, for that point right there? Well, you go up 56, a volume of 56 milliliters. So you're going to go out 2, up 56. So notice that you have to go out 2. You have to go up to the 50 milliliters, which is where it starts. And then you have to go another 6 milliliters, because that's the 2 times 3 milliliters for each marble. 2 marbles times 3 milliliters equals of movement up of 6 milliliters. And where do you end? You end up, when you hit this line, you end up at a volume of 56 milliliters. So you read across here to tell you what volume it is for this point that lands on this line right here. So you end up at 56 milliliters. Now, what if you didn't have the description that went into all this detail that told you what this equation was? What if you just had a couple points? You had 9 and 5. So this goes out, x is 9 units, up 5 units. And this point here is x is 3 units, and up y is 3 units. So both those points, you draw a line through them, and it crosses here at 2 units. So how do you write an equation for if you just know these 2 points? Well, start here. So you're going to measure the change in y, as you're going to start at y equals 3. So you go out here to 9, and you go up 3 units. So this is going to be the start of this side of the slope triangle right here. So the change in this side, the vertical change, starts at 3. So you begin here at 3, and where does it end? Well, it ends at this 5 here. So how many units have you gone up from starting at 3 and ending at 5? So it ends at 5. So the change is equal to 5, that 5, minus this 3. So you have to get rid of the beginning amount, and you end up with that change of 2 units. So this change in the y value right here, the side that measures along the y-axis, that change is 2 units. And the change in the side, in this side, that's the horizontal change, that one also starts at 3, except it's a different 3. It's 3 from the y-axis going this way. This 3 is a 3 from the x-axis going up here. This 3, I would have chosen a different number here to avoid that confusion. Anyway, so the change in this side begins at, or starts at this 3. And then how many units does it go? But we're going to calculate that. But where does it end up? It ends up at 9 units out. So it ends up here at 9. So what is this change along the horizontal axis? Well, it's the difference from where it starts to where it ends. And how do you figure that out? That's 9, this 9, minus this 3. You have to get rid of these 3 units. And that equals a change of 6 units along this horizontal axis. So the change in y, the change along the vertical axis, is 2 units. The change in x, or the change along the horizontal axis, is the 6 units. And so you compare those two numbers, that is the slope. So the vertical change was 5 minus 3 equals 2. The horizontal change was 9 minus 3 equals 6. Then you simplify that to 1/3. Okay, so the vertical change compared to the horizontal change is 1/3. So what does that tell you? It says that this vertical change, 2, is 1/3 of this horizontal change, 6. And that makes sense. 2 is 1/3 of 6. So the vertical change is 1/3 of the horizontal change. So it's this 1/3 right here. And the graph begins at 2. So B is where it begins. It begins at 2 units. So you put those two values together, these two properties together. What's the vertical change for each horizontal change? So for each unit, the vertical change is 1/3 of a unit. And where does it begin? It begins at 2. You put them together in the equation, and you get y equals 1/3 x plus 2. And this 1/3 is m, which is the slope. And this 2 is where the graph begins. It begins at y equals 2. Now you can check that by writing the equation from these 2 points. So if you call this 5y and this 9x, and you remember from before, and this is the direction we're going. We're going to do this more and more. You can take that y and subtract the 3. So y minus 3, that's the amount of change along the vertical axis. And you can take this x and subtract 3 as well. So x minus 3 is the amount of change along the horizontal axis. And what does that equal? It equals the slope. We already calculated the slope. And so what that tells you is that y minus 3, the vertical change, is 1/3 of the horizontal change, which is x minus 3. And once again, you look at this, and that's what you see. This vertical change is 2. That is 1/3 of this horizontal change, which is 6. So you're only going to go up 2 units for every 6 units. So this length is going to be 6 units, and this length is just going to be 1/3 of that, or 2 units. So you get this kind of triangle. This length is 2 units. This length is 6 units, or the number of units, I should say, are 2 units. Number of units here are 6 units. So these 2 units are 1/3 of these 6 units. So the slope is 1/3. So then you can rewrite this as the change, the vertical change is 1/3 the horizontal change. That's what we just said. This vertical change is 1/3 of this horizontal change. That's what this division tells you, is how many times you need this value to reach this value. And you need 1/3 of this value to reach this number of units, or this value. So y minus 3 is 1/3 of x minus 3. And you can work this out. If you have 1/3 of x minus 3, that means you have 1/3 of x minus 1/3 of 3. Well, 1/3 of 3 is 1. So 1/3 of x minus 1. So you have y minus 3 equals 1/3 x minus 1. And so if you're going to subtract that 3, remember you have to add that 3 back. You want to get to what the y coordinate is given an x coordinate. Whatever number they're giving you for x, you want to try to figure out what y is going to be to get to that point that's on this line. To get to that point that's on this line, if they give you 5, how do you calculate it? It's 9. If they give you 3, how do you calculate it that it's 3 also? So y minus 3 is equal to 1/3 x minus 1. Add the 3, subtract the 1 at the same time. So y is equal to 1/3 x, and that 3 minus 1 is 2. So y equals 1/3, whatever the x value is, plus 2. Remember that 2, you're adding the start. You're adding the beginning amount, which is that 2 right there, which matches this 2 right here. It has to. So let's say they give you 5. Let's say they give you 9 for the x coordinate. So 1/3 of 9 is 3. And so 3 plus that 2, you have to go up to 2 units. So they give you 9. 1/3 of 9 is 3. And then you have to from that 3, you have to add the 2 units right here. So it's 3, but you have to add these 2 units that are the beginning amount. So 3 plus 2 gets you up to this 5. So it's really that 3 right here plus this 2 gets you that 5. If they give you an x-coordinate of 3, 1/3 of 3 is 1. So you're going to be at this 1 right here. But then you have to add 2 more units, which is the beginning amount, to get to this 3. So whatever x is, you take 1/3 of that value, and then you have to add the 2 units along the y-axis to get to the y coordinate.